in the cloud. So I'm going to repeat. So you have two files, the one that I send you and the one that, so the one I send you today, which it says chapter 3, and the one that you received before, which is chapter 2, right? So chapter 2, basically, let me erase this. That's the file that I just copied. So so this is chapter chapter 2, and this is chapter 3, right? Chapter 2 and 3. So you are gonna copy. So first of all, you're gonna open another in chapter 2. You're gonna open another spreadsheet. Then go to chapter 2. Sorry, chapter 3. Copy. Edit. Copy. So paste chapter 3 in the new chapter 2. Right? So open another one because there are two different exercises. So go back to the new file, chapter 3. Go to online resource. If you click here, you're going to open a website. So try to click in another cell, highlight all your information, copy, and then paste in the new file, right? So once again, the previous chapter that is called chapter 2 Excel, you can just change the number and set De La Cruz, right? De La Cruz,
Is this
module 1. Okay.
Hello, can you hear me?
Hello.
Yes, I'm asking if is this file on Blackboard?
That is not in Blackboard. I send it via email.
Why don't I? Okay.
What? Hello? Hello?
Professor, actually, I was looking through my email and I never got, I didn't get chapter 2. I got chapter 3. I got the email that you just sent with chapter 3, the Excel, but I didn't get chapter 2.
Okay.
At least I don't find it.
That's good to know. So what I'm gonna do is the following. I mean, if you guys don't receive emails, I mean, I don't know what to do. That's the only way I can connect with you. So you have to call. I mean, and thank you for telling me that you have issues with this.
Well, I received. Well, no. I don't mean to cut you off, but I received I'm receiving your emails. I just did not receive the chapter 2 Excel spreadsheet.
Well, I send it, and then I said, if you go to module 1.
Blackboard. Okay, copy.
Yeah.
Okay.
So also, what I'm gonna do is I'm gonna add this chapter 3. So I'm gonna add the file, which is chapter 3, in chapter 3, of course. So you are gonna be able to have it and then download it. So, okay, that's fine. Okay, so I'm gonna also include the PowerPoints. So those PowerPoints are will have all the information that you need. So of course you have to read the book, and so you have now. I'm gonna make them, put them. So if you don't receive my emails when I said I'm sending emails and you don't do anything, I just cannot do anything else. So please try to fix that issue with the IT department. And if you want me to talk to them, just copy your email, copy me in the email that you send to them. So I don't know if you don't receive the emails or what's going on. it's very common that I send the emails, and I have done it many times. I just see it and I said I'm gonna review it later, and I don't. So that probably happened, and I don't want to point fingers at anybody. So please be mindful, okay? So so today we're gonna do some exercises. So I explained how to use the previous, copy the new ones, and then so you are gonna submit only one file. So I'm gonna check all your assignments in only one file, okay? So today we are going to talk about probability. So let me make this bigger so we can see this presentation differently today. So so today we're gonna talk about probability. This is a very important topic, but I think I have said that before for many for many things. So but this term, this idea of probability is going to be something that we're going to be applying so many times during this course, okay? So so probability measures that is, so it's a measure that is associated with how certain we are of the outcomes of a particular experiment or activity. So probability, you are gonna assign a value that says, well, I am 100% sure, so that means that the fact is eminent. Or you can say, I think that is not gonna happen. So that is that is a zero probability, right? So probability is associated with this measure of a particular outcome when we are doing experiments. So what is an experiment? Well, an experiment is a planned operation carried out under controlled conditions. For example, tossing a coin, flipping spinning a spinner. So this is an experiment. So planned operation carried out under controlled conditions. So if the result is not predetermined, then the experiment is a chance experiment, meaning it's a probability experiment. So it's given by probability and not by things that we are already predetermined. For example, as I said, flipping a fair coin twice is an example of an experiment. So we don't know what is going to happen. So that's what is called an outcome. When we toss the coin and we see that this is a head, so that is the outcome. So that is the result of an experiment, and the sample space is going to be all the possible outcomes. So and these possible outcomes can be represented like a list of possible outcomes. We can use tree diagrams or we can use Venn diagrams. So so this is an example. The uppercase S is used to denote a sample space. For example, if you flip a coin, so the sample space is going to be made out of two different elements, and those are all the possible outcomes that can happen, heads and tail. Okay, so so then we have events. Is any combination of outcomes. Uppercases letters like A and B represent the event. If the experiment is to flip one fair coin, so probably the event is gonna be getting at most one head, right? So if you are flipping the coin several times, your outcome is gonna be your event is gonna be getting at most one head. So when I get the results of this experiment, I'm gonna count for them. So and I'm gonna find the probability of the event. So the probability of the event is going to be, this is the event, and this is the probability of the event. So when I said the event is getting one head, so so the probability of that event is heads over the amount of the elements in the sample space. So the probability of an outcome is the long-term relative frequency. So remember that we were doing frequency tables, probability frequency tables, and we found that the relative frequency accounted for the probability of the event. So probability, in short, is the long-term relative frequency. And probabilities are values that fall between 0 and 1. So we cannot have 110%. That is not possible. We cannot have negative probabilities. Probabilities go between 0 and 1. So 0 means that it's almost impossible, and 1 is certain. So in between, we have something that can be likely or unlikely. If we are in the middle, so there is an even chance that things can go well or not good, okay? So if you flip one coin like several times, like for example, from 2 to 2,000, and then to 20,000 times. So as more as you do this, this relative frequency is gonna approach to 50%, right? So if you have a coin, there are two possible outcomes. One is heads and the other one is tail. But do it 10 times and I'm sure that you are not gonna get 5 and 5. You probably are gonna get a number, a different number. Then increase the number of flipping coins to 100, to 1,000, to 2,000, to 10,000. So you are gonna see that the more you do this experiment, that experiment is gonna approach to the expected value of my event. So so we have some events that are equally likely to occur. So that means that each outcome of an experiment occurs with equal probability. For example, we toss a fair six-sided die. So of course, 1, 2, 3, 4, 5 are exactly likely to happen. So if the die is fair, so then either one has the same probability to occur. That happens also with if you toss a coin and the coin is fair. So you have each one has the same probability to occur. For example, in this case, the probability of heads is 1/2 because we have two different elements. In this case, the probability of let's say 3 is 1/6. 3 is one element and there are 6 elements in the sample space. So the probability of this is going to be 1/6. So also, if you randomly guess the answers to a true/false question exam, so you are equally likely to pass or to not pass the test, right? So probably by chance you answer all of them correct. You can answer 70% correct just by doing this randomly, or you can get a 0. So we don't know, right? So each one is going to be equally likely to happen. So to calculate the probability of an event A, when all the outcomes in the sample space are equally likely, we count the number of outcomes for the event and divide by the total number of outcomes in the sample space. So that's what I was mentioning before. So the probability of A, so is gonna be the number of outcomes of event A divided by the total outcomes in the sample space. In the case of the tails over head, the probability of tails is the number of tails, which is 1, divided by the total of outcomes, which is 2, so it's 1/2. The probability of a 3 here is the number of outcomes in the event, so in the die you have only 1 3, so it's 1/6. So if you toss a fair dime and a fair nickel, the sample space is given by this. So we will explain this later when we do the trees, but so what are the possible things that can happen? So you toss one dime and a nickel, so you can get 2 heads, 1 head and first a tail and a head, or a head and a tail, or 2 tails. So the sample space have 4 different outcomes. So A getting 1 head, and there are 2 outcomes to meet that condition. For example, if my event is getting a head, so I have here, so I have well, here I have one head. So I have two different outcomes when I have one head. So if that is the event, the probability of event A, which is getting one head, is 2 over 4. So 50% of the events include one head, okay? So this is also important. We have been talking about probabilities. That concept basically is telling me that if I have the number of outcomes divided by the sample space, the total outcome in the sample space, I'm gonna find the probability of that event. Once again, this is the basic concept of relative frequency. So besides that, we have 3 different types of probability. So this probability can be named classical or theoretical probability. So in this case, each outcome in a sample space is equally likely. So basically what I described a few minutes ago is the concept of classical or theoretical probability. You have the number of outcomes in event E and then divided by the outcomes in the sample space, and you have the theoretical probability. So, so that means that, for example, if I ask you what is the probability of a head, you very quickly are gonna say 1 over 2. If I said what is the probability of a 3, it's gonna be 1 over 6 in the die. So that is the value that I am expecting to occur. But what happens if I start doing this as an experiment? So that is not gonna be exactly as the theoretical. It's gonna change. If you, as I said before, try tossing a coin 100 times or 10 times and then 50 times and then 100 times and see how the numbers change. So, so we have the theoretical, which is the probability associated to an event, versus the empirical or statistical probability. That is based on observations obtained from probability experiments. So basically here, we're gonna do the relative frequency of the event. So I am gonna do the experiment, and then this experiment, I'm gonna see how many heads over the number of times I'm doing this, right? So, so I'm gonna get something different. So one of the comments I was making is this one. If you flip a coin repeatedly from 20 to 2,000 to 20,000, so the relative frequency of heads approaches to 0.5. So that basically means that the statistical or empirical probability approaches to the theoretical as the sample size increases. As I start doing more and more and more trials, so the theoretical, the empirical or statistical probability approaches very fast to the classical. So that's something that we should keep in mind, because that is called the law of the large numbers. So the law of the large numbers says that as the sample size increases, the empirical probability becomes the classical probability. And then we have something that is also called the subjective probability. So this is intuition, that is uneducated guesses, and or estimates. For example, a doctor might feel that 90%, so that patient has a 90% chance of full recovery. So probably, so one example of subjective probability is when we go out and we look at the sky and we see, oh, it's sunny, it's not gonna rain. So that is a subjective probability. And you can say even, I can say that I have a 90% based on my judgment, there is a 1% chance that it's gonna rain. Am I right? Am I wrong? I don't know, but that's what subjective probability means. So, so that's what I was mentioning, the law of large numbers. As the number of repetitions on an experiment increases, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. So in this case, and I want you to pay attention, very close attention, because here we have two different types of events that we are going to analyze. This event, so the OR event is going to be basically given when, so it's going to happen when we have mutually exclusive events. What does that mean? I'm going to explain it. Part of this lecture is to cover that area. But every time you see the OR in some of the statements that we are going to be analyzing, so very quickly you are going to say, oh, that is a mutually or non-mutually exclusive event. So when we are using the word and, so we are going to be referring basically to independent or dependent events, right? Keep that in mind because that's going to be very important. We're going to be making some, solving some examples, and the little difference between the or and the and is going to make the difference on how you can approach to the problem, okay? So, so an outcome is in the event or A or B if the outcome is in A or B or in both. An outcome is an event A and B if the outcome is in both A and B at the same time. So that's probably not very clear, but we are going to make these concepts more understandable when we are looking at the solution of problems. So so I really want you to remember all mutually exclusive events, and we're going to pay attention on, or we're going to, this and is going to be defining the independent or dependent events, okay? So, and also this is important because we have the probability of raining. For example, you are using, just by using your subjective probability, you say that there is a 1% chance for rain. So what is the probability of not raining, right? So 1% probability of raining. So what is the complement of this? So of course, if I have a 1% chance of rain, so I have a 99% chance of sun, right? So that talks about the complement. So each probability has an associated complement. So the complement of an event E is the set of all outcomes in a sample space that are not included in the event E. So for example, this is event E. So the complement is what is not in that in this diagram. So we denote the complement as E prime. Every time you see a prime in your A prime, B prime, so it's asking you to find the complement. And this is interesting. Remember, we mentioned that probabilities go from 0 to 1. So, so in this case, if I have the probability of an event, let's say the probability of rain is 1%, the probability of sun is going to be the complement. So it's going to be 1% plus 99%. So the point I'm trying to make is that the probability of the event plus the probability of the complement is equal to 1. So that means if I know the complement and I want to know the probability of the event, so all I have to do is to subtract the complement from 1. So I will know what is the probability of the event. So, and conversely, I know the probability of the event, which in this case, I set it in 1% for rain. So, so this 1% minus 100%, that is going to be the probability of sunny, okay? So, and this becomes a little bit more tricky. And when I said a little bit more tricky is because we have conditional probabilities. So a probability that is conditioned to another event. So the conditional probability of A given B is written in this form. So we can say that the probability of A given B, and is the probability that event A will occur given the fact that event B has already occurred. So as I said, that's a little bit tricky because we have to understand that something happened and then a second event happened, but this second event depends on what happens in the first. So, and that's when the idea of mutually exclusive or independent events are important because, so that's important. So far we have the probability, the conditional probability, that is when A happens given that, that B has already happened. Or basically what we usually do is that we look at the probability of B, so something happened when A has already happened. So that's basically what I see in most of the textbooks. So so that means that we have an event A, an event B, and we need to compute B when A has already occurred. So a condition reduces the sample space. So we calculate the probability of A from the reduced sample space B. So the probability, the conditional probability of A and given, so the probability, the conditional probability of B given A, given the fact that A has already occurred, so it's gonna be given by the following. So it's the probability that A and B occurred in sequence and divided by the probability of A. So where A should be always greater than 0. So this probability has to be anything, it cannot be 0. Otherwise, we cannot compute this conditional probability. So let me show you an example. So this is an example of conditional probability. So we toss one fair six-sided die. So we have the sample space. So of course, the die has 6 different faces. And event 1 says let face, so let A be the face is 2 or 3. So you are expecting, if you roll the die, you are expecting to get a 2 or a 3. But then event B is face is even. So I am expecting the expecting the probability of having a 2 or 3 given that the face of the toss or rolling the die is, I know is an even. It's an even number, right? So in this case, we have an even number and we have an odd number. So the probability of this number or the result of this depends on what happens in B. So I know that B is an even number. And if I look at the faces of the numbers of the 6 faces, 3 of them are gonna be even. And in this event, there is only so there is only one even number. So to calculate the probability of getting a 2 or 3, given that the face is even, so we count the number of 2 and 3s in the sample space B, and then we divide by the number of outcomes B, so rather than the sample space. So what I'm gonna do is I am gonna take the even number. So of course, relative to the sample space, this is 1/6. So that's what I have here, 1/6. So this is the number of outcomes that are 2 or 3 and in event in the sample space. And then I have the number of elements in the sample space. So here I have 1/6. So then the probability of B is gonna be 3 different numbers, 2, 4, and 6, because those are the even numbers, right? So this is 3/6. So if I am solving this, of course I can multiply the ends and then multiply the values in the middle and then simplify. I'm gonna have 1/3. So I will have 6/18. So simplifying is 1/3. So that means that in this particular case, I have 1 6, and here I have 3 6. So so I have to divide them to find the conditional probability. And probably that's not the best example I can give you now, but we have another one. I think this is a little bit, I like this a little bit more because we can get some more ideas on how it works. So for example, let me get my notes. We have this case. So the table shows, and this is to find the conditional probability using 2x2 tables. So if you work with people in health sciences, they love to use these kind of tables. So so that is a table that has 4 different things here. So here is the present, if the person is, in this particular case, has a high IQ or a normal IQ. And this is the person either has a gene or the person does not have a gene. So we have this data. So 33 people have high IQ and have the gene present, and 19 people have high IQ and they do not have the gene present. So, so that means that the total number of people with high IQ is 52. The total amount of people with the gene is those who have high IQ and those who have a normal IQ. So we have people with the gene 72 and people who don't have the gene 30, right? So find the probability that the child has a high IQ given that the child has the gene. So there are 72 children who have the gene. So in this case, we have the gene. And so the sample space consists in all these 72 children, right? So of these, 33 have a high Q. So what we can do is here is the probability of the probability that the person has a high Q and a high IQ given that they have the gene present. So in this case, we are doing the gene present with, so this is the intersection of A and B or high Q and gene. So we have 33 people divided by the sample size or the elements in the sample space. So in this case, we have 72. So the probability that the person has a high IQ and then given the fact that has the gene is going to be given by 33 divided by 72, which is almost 0.458, right? How does it look in another thing? Like, let me do this for you. So in this case, I'm looking at the probability of high IQ when the gene is present. So this is the probability of high IQ when the gene is present. So we had 33 people who have high IQ and have the gene present, divided by the persons who have the gene, right? 72. So what happens if I want to know the opposite? I want to know what is the probability that the person has the gene given the fact that they have high IQ. So I'm gonna reverse this. So now my probability of A and given B is gonna be explained by the probability that the person has the gene given that the person has a high IQ. How do I solve this? Well, once again, the intersection between gene and high IQ is 33. So I have 33 people with a high IQ, but I have the persons, so the total of people with high IQ, right? So that is the given. 52, okay? So that's gonna be, you compute the result. So I'm just flipping these two ideas because these 2x2 tables, as I mentioned before, are very good, but we have to pay attention on how to compute the values. So in this case, if the person has a high IQ given that they have the gene. Here is that the person has the gene given that they have high IQ. So this probability is almost, as we see here, 48.5. So let me compute this. It's going to be 32 divided by 52. So we have a 61.5. So this is equal to 61.5, right?
Professor,
So,
I have a question.
yes. Do you have a question?
Yeah.
Okay.
So I understand how you get the 52, but like the 32, I don't get that part.
Oh, sorry, it's the 33. Oh, the 33. Thank you. Thank you. It's this number. Thank you for noticing that. It's 32. Thank you. That was a mistake on my part. Okay, thank you very much. And that means that you are not sleeping in the class. Thank you. So yeah, somebody was asking, how did you get the 32? Yeah, it's 33. It's 33. My apologies. This is live. So we are recording this class live. So we have these issues, right? So once again, this is 33, not 32. Okay. So we have these conditional probabilities. What I recommend you guys to do is to look at this table 20 times and figure out how you solve the case, how these conditionals apply, whether it's be subject to A or vice versa. So so that was very good. So now we are gonna add a little bit more of things here. So why do I want to know these conditional probabilities? Well, at some point we have events that can be dependent or independent, right? For example, if I, well, so two events are independent if the following is true. So that the conditional probabilities are, if I want to know, so I want to know whether the conditional probability, the probability of A given that B has already happened is equal to my probability A. If the probability of B in another experiment, given that A has already occurred, has to be equal to the probability of B. That sounds like a tongue twister. I'm going to explain that. So when that is, so that is true. So when that happens, when we have independent events, so the probability of A and B in these independent events, remember what we saw, I said a few minutes ago, there are or and examples. So this is the and example. So the probability that A and B happen in sequence, if they are independent and we corroborate these two conditions, so the probability of A and B happening in sequence is going to be the probability of A times the probability of B, right? Don't panic too much. Nobody remembers that until you have to solve a problem and see your notes and actually make sense of this, right? So two events are independent if the knowledge that one occurs, that one occurred doesn't affect the chance that the other occurs. So so we have an example here. Two outcomes of the two rolls of a fair die are independent events. So you roll the die, you get a 6, you roll the die, and whatever is going to happen is not affected what happened before. You are rolling a die and tossing a coin, so neither one affects the other. So we are very sure that those are going to be independent events. So we have dependent events when that the conditional probability is not equal to the simple probability. So in this case, we're going to use a different formula. So keep that in mind. So we have dependent, independent, and dependent events. Of course, dependent events are an event that depends on what happened before. We have a couple of examples here. I hope that that is clear. This is clear. So decide whether the events are independent or dependent. So selecting a king from a standard deck, not replacing it, and then selecting a queen from the deck. So you have cards, you take the first card, and that card happens to be a king. So you don't replace it, and then you pull the second card. So what is the probability that that second card is a queen? So here is the conditional probability that B given A has already happened. So this is the probability of the second card. I'm expecting that the second card is a queen, given that the first one has been a king. So of course, when I have 52 cards in the deck, if I take one and don't replace it, so the next round, my probability is going to be 4 kings over 51 because I don't have the full deck because the deck I just took out was not replaced. So in this case, my conditional probability is 4 over 51. If I take the simple probability of B, which is a queen, it's going to be 4 over 52. So in this case, the conditional probability is different from the simple probability. So in this case, I can say that we have a dependent event. So the occurrence of A changes the probability of the occurrence of B, right? So in this case, it's very clear that the conditional probability is different from the simple probability. So we have the counter example, tossing a coin and getting a head. So this is event IA, and then rolling a 6-sided die and obtaining a 6. So the probability of getting a 6, given that a head has already occurred. Of course, that doesn't affect. So that conditional probability is going to be equal to 1/6, right? So if I look at the simple probability of this event, the probability of rolling a 6 is 1 over 6. So that means that the conditional probability and the simple probability are exactly the same. So that's basically what this little thing was telling me. So we have independent events when the probability of the conditional probability is equal to the simple probability. And when that is the case, to find the probability of 2 events occurring in sequence, A and B are occurring in sequence, we are going to multiply the probability of A times the probability of B. And if it's dependent, we're going to multiply the probability of A times the conditional probability of B, given that A has already occurred. So once again, sounds like a tongue twister, but when in fact we solve the problem, is not that complicated. I don't want to say that it's easy, it requires thinking, but it's not that difficult. So we have these dependent and independent events. So so we have another example here. Well, we have an application of this. Remember, when they are independent, I am going to use what is called the multiplication rule. The multiplication rule for independent events is going to be, for 2 independent events, is the probability of A times the probability of B. And of course, I can have many more events. This can be expanded to many things, right? So if I have the probability of B, A, B, and C, I just have to multiply them, and I will find the value for that probability. So I have 2 examples for this. So in the first case, we're going to use the multiplication rule for independent events. So 2 cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king, then selecting a queen. So as I mentioned before, so because these 2 are dependent, so the probability of A times the probability of B, given that A has already occurred. So we have these values here. This is the conditional probability. This is the probability of a queen. So all we have to do is to multiply those things. So, and to see that the king and the queen are happening in sequence. So my formula is gonna be given by the probability of K, so which was the first event, and then the probability of the conditional, which is 4/51. So if I solve for this, there is a 0.6% that this is gonna happen in sequence, okay? So we have another example, even easier. So we're using, again, the multiplication rule for independent events. So a coin is tossed and a die is rolled. So find the probability of getting a head and then a roll. So those are independent events that the one doesn't affect the other. And we stated that when we have these independent events, we're gonna have these probabilities multiplied, right? So in this case, I have the probability of a head is 1/2, and the probability of a 6 is 1/6. So if I divide 1/12, so this is gonna be an 8.3% that I get a head when tossing the coin, and a 6 when rolling the die. So it's almost 8%, 8.3%. That's the probability of that event. So, and this is very important because replacement and not replacement affects the outcome of our experiment. So sampling with and without replacement. With replacement, if each member of the population is replaced after it's picked, then the member has the possibility of being chosen one more time. So these events are independent, and the result of the first pick will not change the probability of the second pick. So in this case, we are making assumptions that the card is not being replaced. But what happens if the card was replaced? Well, then we have the same probability for the two, right? So that's the importance of this. So every time we have, we don't replace, so we are changing the odds for the entire experiment. So without replacement, when sampling is done without replacement, each member of a population might be chosen only once. So the probability of the second pick are affected by the result of the first pick. So these events are dependent, or also called non-independent. So in many cases, in most of the cases, are known as dependent and independent, but some people use the word not independent. Of course, two negatives make this confusing. So it's not, if it's not known whether an A and B are independent or dependent, we are going to assume that they are dependent until we can show otherwise, right? So in some cases, you might be unsure whether this event is dependent or independent, and you can assume that they are dependent. So that happens very often in experiments. For example, pharmaceutical companies are performing an experiment, and they don't know exactly whether the pill is going to depend on something that has happened, so many moving targets. So most of the times they assume dependency in their experiments. So, so that is the idea of the multiplication rule. This is just summarizing what I just said a few minutes ago. So rules of probability, the multiplication rule. So the probability of that two events, A and B, occurred in sequence. So that is the probability of A and B when they are dependent. So, so we have this probability of A given times the conditional probability of B given A. So that's the formula that you should keep very close to you. I always have it in my notes. So that is very easy to determine. Remember that the conditional probability is going to be determined by the elements, like the probability that A and B are happening, and then divided by the probability of A. So let me see if I have an example of this before I continue. No, not yet. So for independent events, the rule can be simplified. So now once again, the probability of A and B, in this case, because they are independent events, is just multiplying the two probabilities. So let me show these examples. So this is using the multiplication rule to find the probability for a particular surgery. The probability that a particular knee surgery is successful is 85. So in this case, so let me just follow this. So find the probability that three knee surgeries are successful. For example, in this case, we have, so the probability of surgery 1 is going to be equal to 0.85. The probability of surgery 2 is going to be also 85, right? So we are assuming that I am a doctor, or I am a patient. I'm going to be the third patient in the room. I am a statistician in the waiting room, hoping that the odds are in my favor. So what are the probabilities that surgery, my third surgery, is going to be successful? So this is the surgery number 3. So it's going to be 85%, right? So applying, because those are independent events, so surgery 2 does not depend on 1, and 3 doesn't depend on 1 or 2. So we can say that the probability of these 3 surgeries, yeah, the probability of 3 surgeries successful, the probability of the 3 successes is going to be equal to multiplying all the probabilities. So that's because they are independent. Probability of A, probability of B, and probability of the last one, right? So that's going to be my probability that the third surgery is going to be successful. So so probably I won't be so bad. I mean, I know that surgeries, there is always a risk and something might happen, right? So, but remember, we were talking about the concept of the complement. So the complement here is going to be the probability of S1 prime, right? So remember, we mentioned that the prime is the idea of the complement. So in this case, if I want to know, for example, in this case, find the probability that none of the knee surgeries is going to be successful. If there is an 85% chance of success in each, so the probability of failure in this case is going to be the complement. So in this case, I'm going to find this subtracting 1 minus my probability of, okay? So I'm going to do this for the 3. So the probability of surgery 2 prime, so it's going to be equal. So I'm going to just copy that. And this is going to be the probability of S3 prime, right? Equal. So the probability of no success success is going to be equal to 0.15 times 0.15 times 0.15, right? Not bad. 0.0, it's almost 0.3% that is going to be a failure. So I will not be surprised. I will be calm. So there is a little chance that there is no success in those knee surgeries. So so that's what we got here. So we depart from the concept of the complement. So we multiply those complements. So also find the probability that at least one of the 3 knee surgery is successful. So at least one. So once again, we can use the concept of the complement to say the probability of at least one good, right? One successful. So it's going to be 1 minus the probability of no success. Ooh. So equal 1 minus the probability of no success. Okay. So so that's very good. So we have this multiplication rule. So remember, when the events are independent, or dependent, we are going to use the multiplication rule, and that multiplication rule has to be thought that if the events are dependent, I will use this formula. And if the events are independent, we're going to use this formula, right? So let's do a little bit of Excel. I think I can advance this for a few minutes. So I copy this table from the book. So, and I really want you to complete all this. So if you have the book, go to page 137. And you can see the table is example 3.3, and you can see the table and some questions. Of course, you have the answer at the end. I'm gonna trust that you are gonna do it using Excel. So you're gonna find these results using Excel. I want to see a formula here. I don't want to see the number. Don't tell me that you copy paste. No, you have to write the formula here and tell me what it is. So there are many questions regarding this. So for example, in this case, this is the simple probability, right? So this is the simple probability. So we have the probability of, well, we have a table. So this is my, my table of values. For example, I have 43 males that are right-handed and 9 that are left-handed. So how many males do I have? Well, I'm gonna add this plus this. So I have 52 males. So I have females 44 and only, and 4 of them, so 44 are right-handed, 4 are left-handed. So if I add these two numbers, so I'm gonna have the total of women. So I'm gonna find how many subjects I have here. So I just click the sum. So that's gonna be very easy because I'm gonna be managing numbers that are very nice, 100%. So this is 43% of the 100. This is the 52 of the 100. So you will see how it works. So also how many, so I have 52 males and 48 females. I have how many people who are right-handed. So we have 87 people that are right-handed, and we have 13 people who are left-handed, right? So I can do something very nice that is gonna be super, super helpful. I'm gonna convert this table into probabilities. So I want you to watch this video and follow the steps. This is a very nice way to solve problems using probabilities. You're getting used to these conditional probabilities. That is a very nice way to make your case. So for example, in this case, I'm gonna do the following. I'm gonna find the probability of a right-hand man, right? So that is gonna be equal to the number of men divided by 100, right? So I'm gonna always divide these numbers by 100. So what I'm gonna do here, I'm gonna put a $sign, right? So the probability of having a male who is right-handed is 43%. So once I have this formula with these dollar signs, I'm gonna do this, and then I'm gonna do this. Okay, 5 seconds, I solve all my tables. So 43% are right-hand males, 44 are right-hand females. I have a 9% males who are left-handed. Only 4% are of females are left-handed. So all the people who are left-handed, males and females, account for 13%. So I can do so many things, right? So I have many good things. So as you can see, the proportion of males is 52. So what I can do here, if, as I said, go to page 137 and 138. So you can find this, and in 138, there are two more questions. Please try to answer them. You have the results. You have to make sense on how the person got these numbers, right? So when it comes to the simple probability, the probability of males is gonna be how many males divided by the sample size, right? How many females is also the same, the number of, sorry. So that's a mistake. So if I want to know the number of males, I'm gonna take the number of males divided by the sample size, right? So I made a mistake, and apologize again. Too many apologies in one day. So the total of females is gonna be, the probability of a female is gonna be the number of females divided by the sample size, right? So what I'm doing here, I did it here, right? You can see 52%, 48%, the percentage of right-handed. So I want to know how many people are right-handed. So it's gonna be the number of people who are right-handed divided by the sample size, and the number of people who are left-handed is gonna be this divided by 100, okay? So it seems that we are running out of time. So so just let me use the last minutes. So far so good. We are working on this. So I'm going to complete this next class. I just need the second part to go through this. Remember, once again, go to page 136, 137, 137 and 38. And there are at least, okay, like 15, 16 different things here that you have to solve. Once again, you have the answer. It's not a matter of cheating. It's a matter of understanding how to get the values. How this person got the 52%? That's what you need to ask yourself. So we have another example here. So for example, well, I'll cover this next class. Let me complete this idea, because this is the theoretical part. So we can do more practical things next Wednesday. So so we have the independence events, we have these examples, and we also look at different things that we can do with the multiplication rule. So once again, we are assuming that these events are dependent or independent, and I want you to keep that in mind. The reason they are dependent or independent is because they are connected by the and, okay? Well, in mathematical form. So we also have this case, that's very simplistic too. Multiplication rule to find probabilities. More than 15,000 US medical school seniors applied to a residency program in 2009. So out of these 15,000 people, 93 were matched with a resident position. So that basically means that 7% of these people did not get the position, right? So my probability of success is gonna be 93, right? But then we have a conditional probability. Out of these 93, 82 of the 93 of the seniors were matched with residency positions that was among one of the 3 top choices. So 93% of the people got a residency, but only 82% found the position that matched their 3 top choices, right? So I want to go to, so I am applying to college. If I am accepted to college, probably I'm part of this 93%. But let's say that in my application, I wanted to go to Lehman College, I wanted to go to Yale, and I wanted to go to Harvard. And I was admitted to Lehman College. So one of my choices was matched in this, within this 93%. So this 82% is condition of this 93%. So find the probability that a randomly selected senior was matched with a residency position and it was one of the seniors' top 3 choices. So once again, we have a match with a resident position, which is equal to 93.93. And this one is equal to 0.82%, right? So, so the probability of A is, well, I think it's explained here. I don't have to do this. So the probability of A in this case is going to be 0.93, and the conditional probability of B, given that A has already occurred, is 82. So to find that A and B happens in sequence, I'm going to multiply the probability of A, which is B matched with a resident position, and then multiply it by the probability, the conditional probability. Adam, you raise your hand.
Yeah, isn't that driven from the formula itself? So if it was like the formula for them being independent is no, dependent. It's like if you want to try to find like the probability of A, isn't it like the regular formula, isn't it PA equal P of A and B over B conditional A, or the other way around? Like let's say you want to find the probability of B given A, it would
Yes.
equal to PA and B over PA.
Yeah, that's hold on. I think I was doing this here in the just give me 1 second. So that's what I was doing here. So those are conditional probabilities.
Yeah. That's the same, yeah.
Yeah, it's exactly the same. So in this case, yes.
Right, you switch.
Go ahead.
But it was switch because you crossed it over. So P over A would be, I don't know how you did it.
Well, that I really don't understand the point that you are trying to make. So A is the fact that the person got the residency, and B is that they were matched, but once so B, the event B is that they got the point, they got one of their 3 top choices. So, but that is condition that they were accepted.
Okay.
Is that clear, or I mean?
No, I was just talking about the formula. I wasn't, everything was cleared, but the formula itself, but is all right. Okay.
If you can send me an email, I would be happy to see. I mean, probably I don't understand exactly the point that you try to make. I will be happy to hear your point. So please send me an email, okay?
No problem.
Thank you. So so we have this. So this is the probability, and I don't have the result, of course. I should have the result. So we multiply the 0.93 times the 0.82, and we have the probability that A and B are happening in sequence. So, and this is just finding the complement, find the probability that a randomly selected senior was matched with a residency position did not get matched with one of the senior top choices. So we know that 82% were matched with a resident position. So this is the complement of the conditional probability. So in this case, the probability of getting one of the 3 top choices given that they were accepted to the residency, so is 1 minus that probability. So the complement is that 18% of the people applied, they were accepted, but they did not get one of the 3 top choices, right? So I think I am running out of time. I think I will stop here, and I will see you guys next Wednesday. So can I spend 5 more minutes? Is that possible?
Sure.
Yes,
Yes.
baby?
Yes.
Okay, so I just want to do a little bit more today, because on Wednesday we're going to be more concentrated on the spreadsheet. So I hope you can watch this part, the online resource. So there is a video here. So you are going to see what happens here.
Statistics and Excel video
Is very easy. So please watch it and try to advance on this, right? So so we have these mutually exclusive events. So A and B are mutually exclusive events when they cannot occur at the same time. So that means that A and B do not share any outcomes. So the probability of A and B happening in sequence is 0. So for example, suppose the sample space 1, 2, 3, 4 up to 10. So is divided in 2 different events from 1, 2, 3, 4, 5. And the other one is 4, 5, 6, 7, and 8, and C is 7 and 8. So A and B, so this and this, are sharing 2 different, two of the same elements. For example, these 4 and 5 are going to be here in this area. So this is the elements of A, this is the elements of B, but then A and B are going to be sharing some of these elements in here. So that's when those events are not mutually exclusive. So they are mutually exclusive because elements of A are not on B and vice versa, and they are not mutually exclusive because there is an so in the middle of these 2 Venn diagrams, so some of the elements are falling in the middle. So so this is an example of mutually and non-mutually exclusive events. So for example, decide if the events are mutually exclusive. So you roll a die, you roll a 3 on a die, and then you roll a 4 in a die. Of course, those are mutually exclusive because 3 cannot be 4 and 4 cannot be 3. So once you roll the die and you get a 3, that's it, right? So the first event has 1 outcome and the second event has also 1 outcome. So these outcomes cannot occur at the same time. However, we have another case, and of course, that has to be not mutually exclusive. For example, randomly select a male student or randomly select a major nursing. Of course, people can be males and can be also a nursing. So that is what is called a non-mutually exclusive event. So in the same fashion that we were using the multiplication rule for independent events, so we are going to be using the addition rule for mutually exclusive or non-mutually exclusive events. So the addition rule for the probability of A or B. Remember that the statement in the previous one is A and B happening in sequence. Now it's happening A or B. So the probability that non-mutually exclusive events A or B will occur if they are not mutually exclusive. So the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B together. So if they are mutually exclusive, so A and B, so the rule can be simplified for the probability of A or B is going to be the probability of A plus the probability of B. So that also can be extended to many number of mutually exclusive events. So using the additional rule, that's a very simplistic example. You select a card from the deck and find the probability that the card is a 4 or an ace, right? So how many 4s are in the deck? We have 4 different 4s. How many aces do we have in the deck? We have also 4. So the probability of 4 is 4 over 52, and the probability of ace is going to be a 4 over 52. So, so in this case, 8 over 52, so the probability that I draw a card that is a 4 or an ace is 15.4%. So we have this also example. So using a roll, find the probability of rolling a number less than 3 or rolling an odd number. So number less than 3, we have 1 and 2, and numbers odd in the die, we have 1, 3, and 5. So 2 belongs only to the first, to one event, of 3, 5 belong to the other event, and 1 is in between. So because this number is in the 2 different diagrams, so the event is not mutually exclusive. 1 is an outcome of both events. So we are going to find the probability that find a number that is less than 2 and find a number that is odd. So the probability that less than 2, so so we have 2 over 6, so we have 1 and 2. The probability of having a odd, we have 3 numbers, 1, 3, and 5 is 3 over 6. And then we have the number that is in the intersection, is 1 over 6. So we add the probability of A, the probability of B, and subtract the probability of the intersection. And I think I abused your time. So I guess next class, I'm gonna continue with this. I'm gonna try to summarize what we did, and I'm gonna do the exercises in Excel. So I really recommend you to do this part and solve this part, right? So if you see this part, you're gonna be very likely and very easily do this part, okay? So any question?
So that you said 137 and 138 is the, like you want us to do it on a paper and send it to you, or what?
No, it's here. So you have to complete what I was doing here. I have the probability of male, female. So there are 17 different things here. So that's
Okay.
what I want you to do. So you use Excel to do it. Don't turn anything on using anything else. Okay?
Oh, so that this Excel you're using right now, is it somewhere, or I have to
I just send it via email, and I upload it in Blackboard. You can find
Okay.
it there. Okay?
Okay, thank you.
Sure, of course. And if you don't find it, please let me know, and I will send it to you.
And if when I'm done, I'll share it with you, or what I do?
I think I opened a Dropbox in Excel. Hold on, this is module 1. So as you can see, upload your Excel assignment. Okay,
Okay, I got you. Thank you.
everything is there. So if you don't find it, just send me an email, and happily will send you the information.
No problem.
So any other question?
Thank you. Have a great day.
Okie dokie.
Mhm.
So any other question, guys? Yes, no, maybe?
Hello, yes, I have a question. At what time does this class start? Like at 6 or 6:15?
6:15, 6:15. I was planning to use additional 15 minutes. It started at 6, but some students are coming out from work, and they can make it only at 6:15, and ends at 7:30. So I use 10 more minutes from your time.
Okay.
Okay. Any other question?